I can't feel my hands. Do 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 do. Can you ever really feel your hands? I don't know. Okay, so we are looking at another lens problem where we're using the mirror lens equation. In this problem, we have an object that's placed 10 centimeters from a 15 centimeters focal length lens. And it's a converging lens here. So we have a double convex lens, it's converging. We're asked to determine the image position and the size analytically and using a ray diagram. So our focal length will be on both sides of the lens here. So let's say, maybe this is our focal length right here, our focal point, that's 15. It's gonna match up to the other side, so I'm taking my fingers to my monitor here and trying to draw this correctly. Maybe if you've got a ruler, you can do this a little bit better. If you double this, that'll take us back here to the center of curvature. We double it on this side, take us to the center of curvature. And in our case here, we have an object placed 10 centimeters. So our object's gonna be right about here, okay? If we quickly draw a ray diagram to just see like where this object should exist, it'll give us a good idea of what we should be doing in this problem. For lenses, and specifically a converging lens, it's like a double convex, we can roll across and strike the lens. Technically, and we'll zoom in for this, technically the light is like doing a bend at the surface and then it's bending again coming out, but we're going to pretend these are ideal lenses. So when it hits, it goes through and it passes through the focal point onto infinity. And the second line that we can create actually starts from our top position and just passes through the exact center of our mirror. Now, if we take a look at this here, it's pretty obvious, well, maybe it's not super obvious, but it's decently obvious that these lines are diverging. They're moving away from one another, which means that I actually need to backtrack these lines in order for them to hit. In this case, we have case number 6, where we're going to be creating a virtual image on this side over here of our scenario. This is a magnifying glass. So let's zoom out because I might have to get a lot of distance to backtrack this. And here, let's try to grab all of this and move it a little bit. Did I lose my mirror? I lost my mirror. Undo. Let's grab all of it and give myself some more space because I might have to really move some stuff. I might have a far distance to backtrack. Okay, so let's backtrack these now. To backtrack, I'm just gonna take a point on the line and then make that line go parallel backwards, very, very long. And then I'll do the same thing here, trying to backtrack it. It looks kind of like that, which means that out here where these lines have intersected, oh boy, this is my image. Which, note, just by looking at it quickly, it is still upright. It's the same direction as our object. So this is an upright image, which by definition means that it is virtual. And notice it is much larger, so we should have a magnification larger than 1. And because it is upright, our magnification should be positive. So let's work through this, determine the image position and the size of this, or what our magnification should be at least. So if we want our lens mirror equation, 1 over f equals 1 over di plus 1 over do. Our focal length is 15, and let's keep everything in centimeters and just get answers in centis. So 1 over 15 equals 1 over di plus 1 over, and our object distance was 10. And now for just solving for di, we can go ahead and do this. We'll subtract 1 over 10 from each side, so 1 over 15 minus 1 over 10 equals 1 over do. Something I notice here is that 1 over 15 is going to be a smaller number than 1 over 10 because it has a larger number in the denominator. So I also want to be careful when I divide each of these and then subtract them. So I'm going to have 1 over 15, which is 0.06 repeating, minus 1 over 10, which is just 0.1. So I'm going to get here a negative value. I'm going to get negative 0.03 repeating, or if you wanted to do common denominators and blah, 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 all that stuff, 30 would be your common denominator there, but whatever. This is going to equal 1 over Oh, I have a typo here. What the heck? That's not DO. This is DI. It's the image we're looking for. DI. Bleh. And then I need to take a reciprocal of each side. So I flip them. I make it 1 over negative 0.03. And when I do that, I get that DI will equal negative 30 centimeters. Now, does that actually make sense? Let's think about it. Well, does the image appear where the light actually is? If we go back to our image, the light is physically down here where the rays are diverging. But we see the image back up here. There is actually no light up here. The light came through the lens and then down. So there's no light up here, but your eye thinks that there is. It thinks that that is where the light's coming from because your eye doesn't understand that light can bend. It thinks light can only move in a straight line. So the image is not where it really is in terms of the light, which means that this value has to be negative. We also see here that if we look at the magnification, negative DI over DO, what we'll find is that we get the negative of a negative, positive, of 30 over 10, and we see that our magnification is +3. So our image is 3 times larger than our object, and as we stated before, since this value is positive, it's still an upright image, it is virtual. Okay, so that's what we see there for that. That's what's going on. That's why we have our negatives here, why they make sense, how they apply to the magnification equation, and what we see just across the board. Okay, so that is it for this one. We are finished. I think we've got 2 more examples to do here in other videos, but for now, adios and take it easy.